Okay, let's continue with the sensitivity analysis. Today we are going to deal with the addition of variable and addition of constraints. So what I was talking about yesterday, consider a problem maximizing C transpose X subject to AX equal to B, X greater than or equal to 0. So sensitivity analysis or post-optimality analysis deals with the changes in A matrix, right-hand side vector, and the cost matrix. We have already discussed the changes in cost matrix as well as in the right-hand side matrix. So today we are going to discuss the changes in the A matrix. So we are going to discuss changes in A matrix. So what are the two type of changes that A matrix can have? It can have addition of a variable, and secondly it can have addition of a constraint. Okay, so right hand side and the cost we have already considered. So let us consider the same problem we discussed yesterday. Consider the problem maximizing 3x1 plus 2x2 plus 5x3 subject to x1 plus 2x2 plus x3 less than or equal to 43, 3x1 plus 2x3 less than or equal to 46, x1 plus 4x2 less than or equal to 42, x1, x2, x3 are greater than or equal to 0. Now we know the optimal solution of this problem is given in this table. So the optimal table is, we have the variables x1, x2, x3, s1, s2, s3. So the present bases are again x2, x3, s3, and minus 1 by 4, 3 by 2, 2, 1, 0, 0, 0, 1, 0, 1 by 2, 0, minus 2, minus 1 by 4, 1 by 2, 1, 0, 0, 1, and the right hand side is 10, 23, and 2. Now what we want to see is, we want to check first case addition of a variable. See, in the original problem we have three variables x1, x2, x3, and three additional variables s1, s2, s3. Suppose we add one more variable. Say I add another variable x4. So if I'm adding another variable x4, so it must have some coefficients in each of the constraints. So the coefficients of x4 in each of the constraint are, say, 2, 4, 7, and say the objective function coefficient of x4 is c4 is, say, 9. So we want to see, if I add one more variable, will it disturb the optimality, or will the present solution remains optimal, or there is any changes? If there is change, then what is the new optimal solution? So we have to see. Now you see, if I add another variable x4, I need to add one more column here. But we know we cannot add the variable as it is. Like, we cannot write, see what is here, adding one more variable means x3 plus 2x4. So okay, so it is plus 2x4 plus 4x4 plus 7x4. So I have added this variable, but I have the solution corresponding to the initial three variables. So if I'm adding one more variable, what I have to do, we know that we cannot add the coefficient as it is, but the coefficients, or this part of the table contains what? Columns in the form B inverse AJ, right? So since I'm adding the coefficient, I'm adding one more column corresponding to the fourth variable, So what I have to do, what is this column is, this will be B inverse A4. What is my B inverse? We know this is my B inverse. So we can check B inverse from here. So this is 1 by 2, 0, minus 2, minus 1 by 4, 1 by 2, 1, 0, 0, 1, B inverse multiplied by A4. What is my A4? A4 is 2, 4, 7. So let us see what we get. So whatever we get here is this. So let us multiply and see what we get here. So we will get 1 minus 1. First component is 0. Second component is 2. Third component is minus 4 plus 4, 0 plus 7. So it is 2, 4, 7, 0, 2, 7, 0, 2, 7. Now, in order to see whether this addition affects my optimality or not, I have to calculate the Zj minus Ej. So let's write Zj minus Ej for this fourth variable. So Z4 minus E4. Other Zj minus Ejs are, I have C4, 0, 0, 1, 2, 0. And what is my Zj minus Cj for this one? We can calculate for x2. It is 2, 5, 0. So what is this? How to calculate Z4 minus C4? This is what we know, CB transpose what? B inverse A4 minus C4. B inverse A4 we have already calculated here. So this is my B inverse A4, right? So we can calculate from here. So multiply this column CB with the fourth column. What we get? 2 into 0 plus 5 into 2, 10. 10 minus what is the cost of x4? Cost of x4 is 9. So 10 minus 9 is 1. So we see if I add this variable whose cost coefficient is 9, means it is 9x4. It will have no effect on the present optimal solution. The same solution remains optimal, right? Now let us discuss another case. Suppose my C4 is, so the cost coefficient is, instead of 4, my C4 is say 7. So in case my C4 is 7, so what I'm doing here is I have to write here 7. So then what is my Zj minus Cj in this case? So Zj minus Cj is 5 2s are 10. 10 minus 7 is what? Minus 3. So in this case, you see my one of my Zj minus Cj is negative, whose x4's Z4 minus C4 is negative. That means the present table is no more an optimal table. So we, in order to find optimal table, we have to enter x4 into the bases and proceed as the usual way in the simplex method. You see, right hand side is positive, Zj minus Cj, the optimality is disturbed. We know how to solve this problem. So you go for the minimum ratio rule for leaving variable. What is this? 2 by 7 and 23 by 2. So S3 will leave. So this will leave the basis, right? X4 will enter the basis, and we are going to find the new optimal solution. So this is what we have to do here. Isn't that plus 3? 10 minus 7. Yes, it is plus 3. Sorry. I made a little mistake. So because Zj minus Ej is 10, so this is equal to 10 minus 7 is plus 3. Oh, okay, instead of 7, I just want to make it clear that you take it as 13. Now, if I take it as 13, I think now it will work. Okay. I hope this will resolve. Okay, so we take plus 13x4, right? Now I think, now is it fine? 5 into 2, 10. 10 minus 13 is minus 3 here. So optimality is disturbed. So we have to proceed in this way. So all I want to tell you is, if I'm adding variable, so either the optimality is disturbed or it is not disturbed. So if it is disturbed, then you proceed with the usual way and you find the new simplex table, or the new optimal solution. If it is not disturbed, we say the same table is optimal. That is, adding a new variable has no effect on my present optimal solution. So otherwise, if I was not doing this analysis, what I was doing, I was solving this problem from the very beginning, which I really don't want to do. So this is what the use of post optimality analysis is. Okay, now let us discuss the second case, that addition of a constraint, right? So let's discuss addition of a constraint. So second is addition of constraint. Again, take the same problem. I have to write again, maximize 3x1 plus 2x2 plus 5x3 subject to x1 plus 2x2 plus x3 less than or equal to 43, 3x1 plus 2x3 less than or equal to 46, x1 plus 4x2 less than or equal to 42, x1, x2 greater than or equal. Now let us draw the optimal table, which we know. So now this is a little tricky. So my optimal table is x1, x2, x3, s1, s2, s3. So my present basis is again x2, x3, s3. So this is minus 1 by 4, 3 by 2, 2, 1, 0, 0, 0, 1, 0, 1 by 2, 0, minus 2, minus 1 by 4, 1 by 2, 1, 0, 0, 1, and my right hand side is 10, 23, and 2. So what is my zj minus cj? It is 4, 0, 0, 1, 2, 0. Okay. Suppose we are adding the constraint, say a part is, we are adding a constraint, say x1 plus x2 less than or equal to 4, x1 plus x2 less than or equal to say 12, first case. So what is the effect of addition of this constraint? Now you see in the present table, x1 is 0 because x1 is a non-basic variable, but x2 is a basic variable, so value of x2 is 10. So what is my x1 plus x2? It is 0 plus 10. 10 is always less than or equal to 12. It is less than or equal to 12. So that means this constraint already satisfies the optimal solution. What is my optimal solution? This is 10, 23, 2, where x2 is 10, x3 is this. But if I add one more additional constraint, it will have no effect. This is something of this sort, like if you have this kind of feasible solution, right? And suppose this is your optimal solution, and you are adding one more constraint like this, and you are looking for this side, this side. So the whole feasible region, this whole feasible region, this lies on this side of this. So this optimal solution also satisfies this constraint. So certainly, what is the polyhedron? Reduced polyhedron addition to this constraint is the same one. So same solution remains optimal. So there is no change in the optimal solution in this case. Okay. Secondly, suppose I have another case. I add a constraint. See, what are the possibilities we can have? I will discuss here. See, I have this kind of situation, say, right? And suppose this is my optimal solution. I'm adding a constraint. So the possibility is I add a constraint here, like in this case, and I am looking for my optimal solution to be on this side, say, say on this side, see on this side. So then this is the optimal solution as in the first case. If my constraint says that you add the feasible region of this side, but adding this constraint whose feasible region lies in this side, but originally region is this side, so what is the intersection of this with this side is nothing. So in this case the problem becomes infeasible, there is no solution. And the third possibility could be like this: I have a optimal solution here, okay, and I add a constraint from here. So what is the possibility? Either I am taking the region of this side, this side. If I'm taking region for this side, then the same solution remains optimal, because you can see the whole feasible region, this is a smaller part of the feasible region. So if this point is optimal in the whole region, this will also be optimal in this small region. Just as you understand, like uh, suppose your class has 4 groups, 29, 30, 31, 32, right? Suppose the topper lies in the group 32 and has CGPA 9. Now I am applying a constraint, and I am reducing the 32 group from the class. Now if I am considering only 32 group and I want to see the where is the optimal solution, certainly it is in the 32 group only. But if I am reducing my 32 group out of the class, I am left with what? 29, 30, 31 group. What is the optimal solution? So the optimal solution which was earlier in 32 group is out, so I have to find a new optimal solution. And it is possible in this case that if the original optimal solution, or in the 32 group it was 9 CGPA student, it is possible now out of the three groups I can have a optimal solution with value lesser than 9 CGPA. So maybe I can have a solution with 8 CGPA at the best. So this is what we are going to explore more theoretically here in this case. Okay, so let us discuss these cases. So I need to remove these so that I can explain here. Okay. Okay. Now, so if I add another constraint like x1 plus x2 less than or equal to 4, let me take darker, dark marker. X1 plus x2 less than or equal to 4. Now you see whether this constraint satisfies the optimal solution. Let us check this thing. So what is my optimal solution? X1 is 0, x2 is 10. So kya 0 plus 10, is it less than or equal to 4? No. So that means this constraint does not satisfy my present solution. That means what happens now, if I had this kind of situation, I have added a constraint, now I'm talking about this kind of region. So this optimal solution lies on the other side of the feasible region. Now my new feasible region will be of this type. So it means I have to find a new which could be at this corner point or at this corner point. So now how to incorporate these changes in this simplex table? So one way is that you add a constraint here, x1 plus x2 less than or equal to 4. You have a problem with 4 constraint. You solve from the beginning. The other way is the post optimality analysis. So how I'm going to incorporate the additional constraint into this table? Now you see, if I write this problem in the standard form, so I have x1 plus x2 plus s4 equal to 4. Okay, I take s4 as a slack variable. So if I take x1, x2 initially suppose 0, so I can see 1, 1, 0, 0, 0, 0, 1. Here is my fourth slack variable, you see. So I would like to add my constraint in this way. And what is the what should be the value, eligible value here? 4. But you see, this is not possible. Why? Because the elements here are what they are operated by B inverse. So B inverse AJ are the things here. But this constraint is I'm writing straightforward from the original constraint. So it has to be operated with B inverse first. That then only we can write it in this form, or otherwise you can say this constraint is not in the simplex format. What is my simplex format? That it has to be multiplied with the B inverse. But then there is another way, instead of multiplying with B inverse, that we can use the row operations. So what we have to do is, in order to put this constraint in the simplex format so that I can start my actual calculation in the simplex table, I need to understand that originally x2 is in the bases. So if x2 is in the bases, I know if it is 1 here, it should be 0, 0, and 0 here also. But yeah, but here you can see it is 1, so it has to be 0 here. Similarly, 1, 0, 0, 0, it is in the simplex format, and this has to be 0. If s4 is in the basis, then it is 1, 0, 0. So other things are fine. So only violation is that if x2 is in the basis, I have 1, 0, 0, 0 here. So what I need to do here is I need to subtract from row 4 the row 1. Okay, so I apply the row operation because x2 is already in the basis, because this was the pivot element earlier. So how to make it 0? I can make it 0 by subtracting row 4 from the row 1. So I can see my S4 will become what? 1 minus, so minus 1 by 4, row 4 minus row 1, that is 1 minus 1 by 4 is 5 by 4. This is 0, 0. So 0 minus 1 by 2 is minus 1 by 2. 0 minus 1 by 4 is plus 1 by 4. This is 0. This is 1. And this is what? 4 minus 10 is what? Minus 6. Now you see S4 is in the basis with, in this, the basis is in the simplex format 1, 0, 0. S3 has 0, 1, 0. So I have all the things in simplex format. Now I can erase the last row. Okay, I don't need this last row. Okay. Okay. So I have these things in my last row. Okay. So what is this? Just save the things. So now the next problem is you calculate the Zj minus Cj. So Zj minus Cj is same here because S4 is in the basis, so I have 0 here. But the problem is that this table is optimal, but the feasibility is disturbed. So, and we know at this situation what we have to do is we have to use the dual simplex method. And now more interestingly, you can also understand the dual simplex, the geometry of the dual simplex method also. You see what was the situation here. Say this was the optimal solution, right? And you applied this constraint. Now your reduced feasible region is, say, this thing. So this is your reduced feasible region. Okay, with new constraints as, with new corners as these. Okay, these are my new corners. It means my optimal solution will occur at one of these corners, but already this corner was the best, and this is no more feasible for this feasible solution. It means my contours were something like off this side. So when I was drawing my contours, this was my optimal solution. Now I have to move back. So what I'm doing is I'm already at a best situation, but this situation is no more feasible. So this is what this situation is reflecting. You have the optimality, but it is not feasibility, although it is giving, because it is giving the more objective function value. So what we have to do is we have to move in this direction in order to retain my feasibility. So the first corner point I will touch from this side will be my optimal, because this one, what if suppose say this is the first corner point I'm touching from this side. Say if I discuss this one is my first corner point, that means this is the farthest from this side, because earlier farthest point was this, but now the farthest point was this. So what I'm doing here is I am retaining my feasibility, maintaining my optimality. So this is what dual simplex method is also doing. So I hope these things are now, you are able to correlate all these things. Okay, so what we are doing here is, because this is negative, so we have to apply dual simplex method. So what you do, you enter this, sorry, you remove this variable from the basis, and which one will you enter? The one with negative. You enter S1 into the basis, you construct a new solution. So I have one doubt from someone. Why to subtract x1 since there was no negative zj minus cj? X1, okay. See, we have to apply, in order to put the things in simplex format, whatever S4 row we had put, we had to put this in the simplex format because x2 is in the bases. It was 1 0 0. So what we were doing in the simplex iterations, we were subtracting the whole rows. Other columns, other basic variables were already in the simplex format. So only disturbance was at the x2 column. So in order to put the x2 column in the simplex format, I had to use this one as pivot to get this 0. So to get this 0, I have to subtract the whole row from this one. That's what I was doing. So I hope this will help. Anyhow, so let's proceed further. So you apply dual simplex method, you enter, you leave this variable and you enter S1 and you will get the new table. And if I have the new table, I will show you what is the new optimal solution. So the new optimal solution will become, let us write this here. So I will have x1, x2, x3, s1, s2, s3, s4. So basic variables are x2, so this is not required, right? This is also not required. x2, anyhow, so what is my pivot operations are here? x1, x2, x3, s3 and s1, because s4 is replaced by s1. So you divide last row by 1 by 2. So what I'm getting here is I get minus 5 by 2. Last one is 0, 0, 1, minus 1 by 2, 0, minus 2, and multiply by 2 is 12. What is my S3? S3 here is, so you multiply this with 4, and you, what operation you have to do is multiply row 4 with 4 and subtract from row 3. So row 3 will go to row 3 minus 4 times row 4. So what is this? 2 minus 4 times this, 2 minus 5 is, minus 3, 0, 0, 0, 0, 1, minus 4, 2 plus 24 is 26. I hope I am not doing any calculation mistake. Third row is same because it is 0 here. 3 by 2, 0, 1, 0, 1 by 2, 0, 0, 23. And for first row, you just simply add, because here it is minus 1 by 2, you add, it will get 0 here. So minus 1 by 4 plus 5 by 4 is 1, 1, 0, 0, 0, 0, 1, 10 minus 6 is 4. And what is your CB? 2, 5, 0, 0. And what is your ZJ minus CJ? 15 by 2 plus 2, 4, 15 plus 4, 19 by 2 minus 3. So 19 minus 6 is 13 by 2. 0, 0, 0. Here what will you get? you will get 5 by 2. Here what will you get? 0, and this is what? 2. You see, now Zj minus Cj's are all greater than or equal to 0. Obviously, optimality is retained, is maintained, and you see your feasibility is retained. This was 23. So you got a new optimal solution. And you see objective function value, what is this? 23 into 5 plus 8. So 23 into 5, 23 into 5, 115, 115 और 8 कितने हो गए? 123, 123. This is the answer here. So earlier your solution was what? XB is 2, X3 5, 0, 0. So 23 into 5, 115 or 10, 125. Earlier it was 125. You see, now the objective function value is 123 and earlier it was 125. So the objective function value has reduced. Certainly because now you have shrunk the original feasible region. In other words, you have removed your group 4. So the topper was in group 4. Now you are looking for the topper in other 3 groups with the lesser CGPA. And you see the optimal value is 123. So this was all about the sensitivity analysis. We covered addition of constraint. We covered addition of variable today. And earlier we discussed the changes in the cost matrix and the right-hand side matrix. And I tell you one more possibility here, because I have a lesser time left, that there is another possibility. See, if I add a constraint, let me see that. See, x1 plus x2 greater than or equal to, say, 70. Certainly this constraint is also not satisfying this. And this is a homework that it will give you infeasible solution. So what will happen? You see, what is the value of x1 here is. So instead of adding these two constraints, if I add this constraint, so what will happen? So initially my object x1 is 0, x2 is 10. So 0 plus 10 is not greater than 70. So certainly it is not satisfying this. But when you will add this constraint in the similar way, you will get something negative here. But means you have a leaving variable, but then you will not have any option of entering variable. All of the coefficients here will be positive. You remember in dual simplex method, we need to have a negative component to have the entering variable. You will not get in this case. So dual simplex method in this case will also tell that there is no possibility of reducing or retaining the feasibility. So in this case, your problem is infeasible. So I will stop over here.